Okay, this lecture 4 continues panel data methods, and many of the definitions and issues are the same as the linear case, although not surprisingly, it's more difficult to handle nonlinear models. I think there are just about as many slides, so I guess I'll have to move along more quickly, but a lot of the discussion about kinds of exogeneity assumptions for linear models carries over here as well. So I'm going to start with some stuff that's not so new and try to make a bridge to the way that the econometrics literature is thinking about some of these issues. There still are large classes of models where we don't have any great solutions to handling heterogeneity in a completely unrestricted way. And so some simple strategies have been used, and again, they have been looked at from a different perspective somewhat recently. So before talking about estimation issues in model, you have 15 seconds to leave the room before it blows. Before we talk about parametric models and assumptions, I think it's very useful to just start at a general level and ask what it is we should be interested in when we look at nonlinear models with heterogeneity. And it's easy to say, well, if we have a parametric model, we're interested in parameters, and we're interested in the distribution of the heterogeneity. But in some leading cases, those two things are not separately identified, and in fact, there's no real hope of estimating each. And so the issue becomes, what can you learn when that's the case? So the starting point is to, again, specify what looks like a contemporaneous relationship in one, where D denotes distribution. So this is conditional distribution, conditional on some observed covariates and then some heterogeneity. And again, X at this level could contain lag-dependent variables. It does not contain things that we would typically call simultaneously determined or measured with error, because we're conditioning on them, so we assume that this is the object of interest. Tomorrow, when I talk about control function methods, we'll look at the kinds of sources of endogeneity that this rules out. So if we look at some feature of this distribution, say the median or the mean, I'm going to focus on the mean for now. We're usually interested in partial effects, and in 2, I've just defined the partial effect of the conditional mean function m with respect to one of the x's, and of course if xj is not continuous, then we'd be just looking at differences. And this partial effect in this nonlinear model depends on the unobserved heterogeneity. So immediately we have to ask the question, well, even if we knew the function m, and we can observe the covariates x, so we know which values are interesting to plug in for the x's, what should we do with the unobserved heterogeneity? And of course, if we know a lot about the heterogeneity, for example, its complete distribution, then we can plug in values that are sensible, like the mean or quantiles or a certain number of standard deviations away. And one common partial effect is to say, well, we're going to estimate the partial effect evaluated at the average heterogeneity, which would be in equation 3. So notice that this is defined for different values of x's. So what we're doing here is trying to figure out what to do with the heterogeneity, not the covariates, because we know what to do with those. We presumably have interesting values that we are going to eventually plug in. We may do some averaging out of those later on, but that's easy compared to the problem of what to do about the unobservables. Now, it's pretty widely understood that evaluating something at a mean and a nonlinear function at a mean and taking the mean of the nonlinear function are not the same thing. In fact, they can be quite different. So this other quantity of interest, which has various names, it's been called the average marginal effect, the average partial effect, and that's in equation 4, which says, well, we have the partial effect as this function of unobserved heterogeneity, and now let's just average across the population. The first place I saw this was in Gary Chamberlain's Handbook of Econometrics chapter. And he actually made the point that 4 seemed more interesting to him than 3 because 3 essentially applies to none of the population if heterogeneity is continuously distributed. And so what are you estimating really in 3? You're putting in some measure of location, whereas 4 at least takes a quantity and then averages out across the heterogeneity. It just so happens that you can identify 4 much more often than you can 3 anyway. So as it turns out, focusing on these partial effects where you average out the heterogeneity leads to situations where you can actually learn something, whereas in part 3, often we won't actually be able to either estimate the heterogeneity, the mean of that distribution, or we won't be able to identify the function, the regression function, separately from the heterogeneity distribution. So as I said, there's an identification issue that we'll be talking about. Now, this average partial effect is closely related to what Blundell and Powell called the average structural function, which it's just a matter of taking the derivative through the expectation, basically. They just say, let's start with the mean function, average out the heterogeneity. That, of course, leaves us with a function of x, and then when you take the derivative, you just pass it through, and then, of course, you get 4. So these, for practical purposes, are the same thing. If you want to look at discrete changes, then you look at discrete changes in the average structural function, okay, and instead of taking derivatives. So there's some consensus that this is an interesting quantity to look at. And certainly, one of the benefits of it is that it's something that we'll be able to compare across lots of different models. Basically, any model where we specify the same covariates and the same response variable, because now we have something that just depends on observables. And so we can ask, well, if we use a linear model, what are the partial effects? Usually, they don't depend on heterogeneity. And then we can compare a nonlinear model, average out the heterogeneity, and see how things stand there. As we know, it's trying to compare parameters across nonlinear models is often not an especially useful exercise. We know now that you don't just compare magnitudes of probit and logit coefficients without doing some adjustment to account for the fact that they have different implicit scales, and the same thing is true here as well. Okay, so if we go back to standard kind of parametric models, how do these definitions compare? Well, a very common setup is the so-called index specification, such as in 6, where the x's are assumed to appear in a linear index form. So xt beta is plus c is the index, so everything is additive, but it's inside this nonlinear function g. Certainly, binary response models take this form, as do lots of other models. And then, of course, the partial effect is just given in 7. And if we know that cap g is something like a strictly increasing function, then, of course, its derivative is positive, and the coefficient beta j gives us the direction of the effect. Okay, and if we take the ratio of the two partial effects, we get the ratio of the parameters. And so we can't learn about the magnitude of the effect of xj specifically, but we can take two continuous variables and ask what the relative effect is. That's given by the ratio of the coefficients, and certainly we get the sign of the effect. But if we want to know something about how big the effect is, you can see that in equation 7, the heterogeneity still is there, and we have to do something with it. We can try plugging in arbitrary values, but we don't know whether we would be in the interesting range of distribution of heterogeneity in the population. So we have to have some way of figuring out what to do with that. I shouldn't say we have to. There's actually a huge body of literature in econometrics that actively asks the question, how do you estimate beta j without making distributional assumptions on the heterogeneity? And so the idea there is to find ways to estimate directions of the effects and relative effects without actually trying to seek the magnitude of the effect. Okay, so lots of so-called semi-parametric literature actually has that as its goal. And I'll mention the distinction again as we go through this. Okay. Now, even more recently, Altanji and Matskin have defined what they call the local average response. And unlike the average partial effect, which could be called ex post, I suppose, a global average response, this looks at the partial effect. So if you look at the piece in equation 8 without integrating it, then that's just what I called theta sub j as a function of the covariates and the heterogeneity. And what the average partial effect is it averages across the entire population. It averages out the heterogeneity. Whereas this just averages out the heterogeneity at the value of the covariates xt. So this is a local effect in the sense that you're just averaging out the heterogeneity for units that are, well, literally in this case, at the value xt already. Not surprisingly, this is harder to identify, but the Altanji and Matskin paper shows how to do that. I'll talk about that a little bit with focusing more on flexible parametric strategies. Okay. So again, let me just remind you at this point, none of these definitions of partial effects depend on whether the x's, we haven't assumed any kind of exogeneity assumptions on them at all. So whether we're in a dynamic context or even later tomorrow when I talk about models with contemporaneous endogeneity, how you define the partial effects doesn't matter. Okay, the question is how do you estimate them? And then, of course, that's where various assumptions come into play. So I can run through the next stuff pretty quickly, I think, because instead of being stated in terms of conditional means or linear projections, as in the linear model, we just state things in terms of conditional distributions. So the strict exogeneity assumption is given in 9. Again, once you condition on the heterogeneity and the time t x's, none of the other x's matter. The sequential exogeneity assumption is in 11. Again, only x. Now we're just conditioning on the x's up to time t. So it's certainly a more palatable assumption in a lot of applications because it's often intended as opposed to the strict exogeneity assumption. It really gets hard to allow for just sequential exogeneity in nonlinear models, unfortunately. They're really, the strategies that are available are basically to write down joint likelihood functions and then grind them through. And basically, we'll see why that's true. Except in special cases, there are no simple differencing operations that will eliminate the heterogeneity, leaving you with some simple moments to use in a method of moments procedure. Okay. Now, an assumption that I didn't talk about much, I guess I mentioned it in the linear case, is the so-called conditional independence assumption. And the reason I didn't mention it much in the linear case, except by way of referring to making inference robust to serial correlation, is because it really doesn't affect one's ability to estimate either the parameters of the regression function or if you wanted to, well, actually, that's not true. It doesn't affect that. I suppose it would affect the ability to estimate features of the heterogeneity distribution. But see, the partial effects don't depend on heterogeneity in that case, and so that you're much less interested in that particular exercise. In nonlinear models, what's happening over time plays a key role in whether you're able to identify the heterogeneity distribution and the parameters in the model or not. And in fact, this is, I think, one of the main reasons why when you see models such as random effects probit used, typically the full set of conditional independence assumptions are used because that way you can identify all the parameters. So the condition stated generally is in 12, which You can relax this depending on the nature of the model, but this is the most straightforward statement at a general level, and that is the y's are independent once you condition on the observable x's and the unobserved heterogeneity. Of course, if you don't condition on the heterogeneity, then the y's generally won't be independent because the heterogeneity is there time period after time period. So this is analogous to imposing the no serial correlation assumption in the linear case. Okay? So as I said, that assumption plays a key role in being able to determine, separate out heterogeneity distributions from parameters. Okay, so then we basically covered this also. The so-called random effects assumption is that the heterogeneity is independent of all the x's. This identifies, interestingly, the average partial effects, not surprisingly, because, in fact, the average partial effects are obtained from the regression of y on the observed covariates. If the heterogeneity is independent of the x's, you can't really tell the difference between having heterogeneity there and just having a different functional form for the mean response. So it would be quite surprising if somehow you weren't able to identify something interesting just by adding in heterogeneity that's independent of the covariates. So the question is, what is the interesting thing you can identify? And the answer is the so-called average partial effects. Okay. So in the leading cases, as I mentioned, random effects probit, random effects tobit, with normally distributed heterogeneity, the very standard models, you can't identify the things you want without conditional independence and then specifying a parametric distribution for the heterogeneity. Now, I mentioned before a middle ground between so-called fixed effects and random effects. And this is typically called the correlated random effects framework, where you restrict the distribution of heterogeneity given the x's in some way. And depending on the model and what kinds of assumptions you're willing to maintain, it leads to different procedures. But the common feature is that there's some restriction placed on this distribution. There's a trade-off between how flexible a function it can be in terms of the x's in all of the time periods versus how many restrictions you have to place on the shape of the distribution. And in fact, in 15, I show a restriction that is sufficient for identifying the average partial effects without further restricting the distribution. So it's the key restriction is that the distribution of heterogeneity depends only on the time average. It doesn't depend on the deviations from that separately. Okay? It's a restriction, and you don't have to make this restriction in linear models to get anything interesting. But we'll see the role it plays in estimating partial effects. Of course, as you get more and more time periods, you can allow the heterogeneity to be correlated with more features than just the time average. And this is one of the insights in the Altanji and Matskin paper, is to allow the heterogeneity to be related to other features of the time series properties of the covariates. So you could imagine, instead of just saying the heterogeneity depends on the x's through the mean, it could depend on them through the mean and the variances, or the mean and some trend parameters. There are lots of things you can do to then free up these restrictions that are common in standard applications of the correlated random effects probit and tobit and so on models. And of course, if you have a small number of time periods, what you can do is limited. So in 16, this just states this general idea that if you have a set of essentially think of these as sufficient statistics for the distribution of the covariates over time, putting them in W. If you think that you have that such that describes the relationship between the heterogeneity and the x's, then there's a lot you can do. Okay, the way the so-called fixed effects assumptions are, they really fall into two classes. One is that you find a sufficient statistic to condition on so that you eliminate the heterogeneity. And the other one is that you actually treat the heterogeneity as parameters to estimate. Or, if you're not really thinking in that way, you're doing it because you don't want to specify anything about the distribution of the heterogeneity. Okay? And I'm going to mention, hopefully at the end, some recent work that's been done on that kind of approach. Okay, the nonparametric identification of the partial effects. I wrote this example. I'm just going to state quickly what the point of this example is. It's a probit model with unobserved heterogeneity, and if the standard textbook take on this model is that if you omit the heterogeneity C and do a probit, then you get an attenuation bias in the resulting parameter estimates. Okay? C is independent of X and normally distributed, and you think, wow, if this were a linear model, whether you had C in the model or not, it could reduce the error variance, but it wouldn't cause bias in any parameters. But in the probit model, what happens is you get this scale factor once you integrate out C. So in 19, it shows the probability that you can actually estimate, and of course that means you're going to estimate these scaled coefficients. Well, it seems a little odd that somehow things break down in this case. As I said, how can adding heterogeneity that's independent of the covariates really cause serious problems in this kind of model? And the answer is, if you focus on the parameters themselves, then you're kind of, I think, misled into thinking that there's some bias here in what you've done, when in fact, if you focus on the partial effects, you see that in fact the attenuation bias is exactly what you want. That is, it is exactly the scaled parameters that show up in the so-called average partial effects. I suspect not many of you have actually worried about this problem when estimating a probit. Gee, is there unobserved heterogeneity that are causing? Well, maybe you have, but the point is don't, because it's a red herring. Okay. Okay. So focusing too much on parameters is not necessarily a good thing. The other example here is actually one that Jin Han had in a comment on a paper by Josh Angris, and he basically introduced it as a puzzle, and that is that if you start with the unobserved effects probit model in equation 20, and then basically make the strongest assumptions you possibly could, which is that the heterogeneity is independent of the x's, 2 time periods, you could even have the x's always be 1 in the second time period and always 0 in the first. In fact, that's what his example did. But don't make a distributional assumption on the heterogeneity. Okay, and the question is, what can you identify in under those very strong assumptions, except dropping the heterogeneity assumption? And the answer is beta is not known to be identified. Okay, so you can't estimate beta, basically. But this seems a little strange because you've imposed these strong assumptions. So the question is, what can you identify? And the answer is you can identify the so-called average treatment effect. And a consistent estimator is just used the difference in means estimator that we would use from a basic difference in difference analysis. So the point is, in nonlinear models, it's quite easy to get, I think, too tied up on parameters. There's a third example, but I'm going to skip by it because I'm not going to have a lot of time as it is. Okay, so the question is then, if we can't identify parameters, and sometimes it's wrong-headed to try, then what should we be doing, or what can we do? And the answer, one answer is that we can actually identify the so-called average structural function quite generally, which means we can identify the average partial effects. And the argument is quite simple. In fact, it's so simple I wrote it in 3 lines. And that is that if we're assuming that the heterogeneity distribution, conditional on the x's, depends on in those x's in a restricted way, so in this case on just the time averages, then you can use a simple iterated expectations argument to show, well, what you can do is condition on those observed things, the xi bars, and then you average those out. Averaging the xi bars out is easy because those are observed. So you take the problem where you had unobserved heterogeneity and you basically turn it into one where the xi bar, in a sense, is a proxy for that heterogeneity. of course, if you started with a structural model, making that replacement does not leave you with a function that's going to in any way necessarily look like the original model you started off with. But the point is, don't be so uptight about that. Just say, I'm happy to estimate this. Okay? And I should say this is a view that that is not entirely embraced in the econometrics or economics profession. We like parameters, right? But anyway. Okay, so the point is, if we have this, then the way the average structural function can be estimated is down in 22. Okay. The question is how are we going to estimate this function R, this conditional mean function? Well, as it turns out, again, the argument is simple, and it's just given in a few lines leading to 23, is that this function that we're trying to estimate, which identifies the average partial effects, is in fact just the mean response of y conditional on the observed things, which we can estimate in a variety of methods, using a variety of methods. We could use parametric methods, we could use nonparametric methods. So once we know that the expected value of yit, well, actually what we're going to use is in equation 24, is the regression of y at time t on the x's at time t, and in this case the time averages, is exactly the thing that identifies these so-called average partial effects, or the average structural function. So, this actually, this is liberating, and one should embrace it, I think, and say, look, all I have to do is estimate this thing, and then I'm going to average out the xi bars, and now I have something I can compare across different models, instead of saying, gee, my parameters changed by a factor of 2, what should I do here, when that kind of comparison usually isn't very meaningful. So, as Altanji and Matzkin pointed out, you can now identify this average structural function by just averaging, by just having one time period, as long as you can get the average on the x's, the time average on the x's. You could do it with one year of data on y, because it's identified by 24. Of course, you can see immediately you need some time variation in the x's. This is all depends on the fact that you have some time variation. You can always add things that don't vary over time, but then, how you interpret those coefficients is, those partial effects is not clear. Okay, so when I mention briefly the specific examples, it will suggest things that I think may seem fairly radical, and that is to just take the usual kinds of functional forms and make them more flexible in ways that make sense and are easy to estimate, and then compute, then average out the whatever sufficient statistics you've conditioned on to get to that point. Now, with dynamic models, things are pretty much the same in terms of what we want to estimate, but there's this additional issue of how we account for heterogeneity and its correlation with the so-called initial condition. So in the notes, I pretty much focus on the case where there's a single lag of a dependent variable, and then there are strictly exogenous explanatory variables. In addition, that's just more or less notation. Of course, as you add lags, you need more time periods. So the question is, how does one deal with the heterogeneity in this situation? Well, basically, you can try to treat them as parameters to estimate. That doesn't work so well in dynamic models unless you have a fairly large number of time periods. You can try to estimate the parameters using a kind of conditioning argument on a sufficient statistic. It's quite a bit harder in the dynamic case, although there are a couple of specific models that you can do it for. Or you can use a correlated random effects approach, which is to either approximate the distribution of the initial condition and then model the distribution of the heterogeneity given the strictly exogenous variables. That's what's in 3 up there. And then this is the likelihood. So you have a joint likelihood conditional, which includes the initial condition. Or you can specify just this, and then once you integrate that out, you get a model of the distribution conditional on the initial condition. as it turns out of these choices, 4 is the easiest for the standard kinds of models because it leads to things that you can trick random effects software into estimating, for example. And at some level, the question is, we're trying to model the relationship between something that's unobserved, conditional, and something that's observed. It's never restricted by the structural model because the distribution of the initial condition could basically be anything. So, you have some choices, and you can choose something harder or easier. Okay. So, in terms of applications to specific models, the so-called unobserved effects probit model starts with equation 27. And again, ideally, we could estimate the parameters under that assumption, or the partial effects more precisely. But that probably should say conditional on all the x's, since I don't state that separately. So there's a strict exogeneity assumption there that isn't evident from that equation. And then the so-called Chamberlain-Munlach device is to model this in the relationship between the heterogeneity and covariates in this way that looks pretty restrictive, actually. In fact, Chamberlain suggested not imposing the time averages in that equation, but allowing the x's in all time periods to have their own coefficient. Remarkably, when you do this, at least in a couple of examples, even though the coefficients are all over the place, when you actually compute partial effects, it turns out that it doesn't seem to matter whether you allow for that generality or not. But of course, and in the linear case, we know you would get exactly the same answer. So there's a hint there from the linear case that maybe how you do that is not terribly important. And then under the assumption of serial independence, you can estimate all the parameters and then compute partial effects at any value you want. As I mentioned before, the so-called average partial effects are identified more generally. And the thing we can drop is we can drop this assumption of conditional independence. So Chamberlain made this point, and he of course didn't call it a name, because why should you call something a name that's fairly obvious? But basically, in 29, when you work this through, the so-called average structural function depends exactly on the scaled parameters that you would estimate if you just do a pooled probit. So instead of doing a full maximum likelihood, joint maximum likelihood, where you would estimate the variance parameters separately from the regression parameters, this just estimates the scaled coefficients directly. And again, you might say, well, does that not give you the estimate of the thing you want? Well, it does give you an estimate of the partial effects. As you can see in that sum there, what's being averaged out is xi bar. Xt is the fixed argument that we're going to take derivatives or changes with respect to. And so the xi bar just gets averaged out there. And those coefficients, those scaled coefficients, they can be from a random effects probit, but they could also just be from a pooled probit. And then you have dropped the assumption, which is a pretty strong assumption, right? That conditional on heterogeneity, there's no serial correlation. That's the nature of the assumption, which we see violated all the time in linear models. So there's no reason to think it might be in nonlinear models. Okay, one comment is that this all goes through if you were to replace the binary response with any kind of variable that could have an expected value that is like a probit function, so a fractional response. And of course, and in that case, full MLE is quite difficult because it's not even clear how you want to model that distribution, whereas this method using quasi-likelihood is trivial, basically. Okay, so a more radical suggestion would be to say, well, I just went through this argument that you can estimate the average effects if you just estimate this expected value at the very bottom of the slide and average out. So so a radical suggestion would be to say, well, look, I don't really know the probit model and the probit function in the structural model is right anyway. It's just an arbitrary choice, right? So why not make the assumption of a probit model when it's convenient? That is, once I've conditioned on xi bar instead of on the unobserved heterogeneity. So again, this is I'm perhaps extrapolating more than Altanji and Matzkin intended, but I think this is completely in the spirit of saying, look, once you know that the partial effects are coming from that thing on the left-hand side, averaged out across xi bar, why not just estimate that in some flexible way and then see what the partial effects are? And then that becomes comparable whether you put phi there or the logistic function or some more complicated function. Everything's going to adjust to make, in many cases, the estimated partial effects quite close. Okay, whereas the parameter estimates would, of course, be all over the map. Let me just give you one example. There's a table in the notes that lists all of the various trade-offs with the different kinds of methods, and I'm not going to talk about so-called fixed effects logit here, since I'm really running out of time. But let me just give you this one example from the notes. It uses data from Che and Hislop on women's labor force participation, and the variable I focused on here, which of course is being assumed to be strictly exogenous, conditional on the heterogeneity, is the number of children. If you do a linear fixed effects analysis, you get that estimate at the bottom. Okay, that's the effect on the probability of having one more child, of being in the labor force, controlling for unobserved heterogeneity. If you do pooled probit without accounting for the heterogeneity, you get a much larger effect. If you do the pooled version of Chamberlain's correlated random effects probit, you get spot on the same estimate you get with a linear model. Okay, now this is averaged across all of the x's in all the time periods. Okay, so this is truly one reported number. It's an average effect, and maybe this would, certainly this would change if you go out in the tails of the distribution a little bit. But when people like Josh Angris say, well, for estimating average effects, a linear model is as good as anything. Well, it's when you see numbers like this, which are now comparable across all models, you wonder. If you do the full maximum likelihood, the magnitude of the effect is a little bigger, but certainly not statistically different from the linear model or the pooled probit with heterogeneity. And then the fixed effects logit coefficient is minus 0.644. But so you don't know really what to do with that. It's a coefficient on a discrete variable. It doesn't make any sense to say, I should be using logit because that number is bigger. That number just tells us the effect is negative. And it's not a continuous variable, so you can't really take the derivative and compare it somehow. So I like the other estimates myself because I want to know, basically, if you have one more child, what is the effect going to be on the probability of being in the workforce? Okay, I will jump. So this same strategy, as I mentioned, can be applied to a dynamic model. So in equation 35, the assumption is exactly the one that allows you to basically plug in an extended set of regressors and use random effects probit. Now, the argument for being able to do this is a bit subtle, and I invite you to read the notes or find the reference in the notes on this. But it works out, and the method is to add the initial condition and then the entire history of the exogenous covariates to the probit, and basically then estimate it by random effects probit. Okay, now in this case, there's no relaxing the no serial correlation assumption. This assumes that the dynamic model is correctly specified. And then as it turns out, as luck would have it, the coefficients you estimate from this turn directly into average partial effects. And just to give you an example of what happens with this Che and Hislop data, now this model has a lag-dependent variable, which is labor force participation. You want to get at an estimate of how big the state dependence is, right? Those are given at the bottom. Using a model that accounts for unobserved heterogeneity, as in equation 35, gives state dependence of about 0.26. So what that means is average, when you look at the probability of being in the labor force at time t, conditional on being in the labor force at time t minus 1, and then you average out the unobserved heterogeneity and the observables, it's about 0.26. If you don't account for the unobserved heterogeneity, it jumps up to 0.837. So this is this widely recognized fact that usually if you don't account for heterogeneity, what you estimate as the amount of state dependence is much stronger than when you do account for heterogeneity. And of course, what I can't tell you, at least not yet, is how this compares to different methods. I also can't tell you the standard error for that because the bootstrap takes a long time to run in this case. Okay, so, well, I guess I'm just going to jump way over to comment quickly on this method of so-called estimating the fixed effects. That you can read, there are many more methods for particular nonlinear models that are described in the notes. Clearly, I was way too ambitious for this set of slides. Recently, this has made a comeback because you can't get very far trying to condition on sufficient statistics to get rid of the heterogeneity. And I guess what I'm arguing here is, even if you could do that, as in the logic case, if you don't assume a lot, sometimes you can't learn very much. And so I would argue that even if you could find a sufficient statistic, the question is, does it deliver what you really want? Well, one possibility is to just say, we're going to see what happens if we estimate the fixed effects as parameters, acknowledge that there's this incidental parameters problem, and try to fix it in some way. Okay, the problem is we're trying to estimate a heterogeneity for each individual with a relatively short time period. Well, as it turns out, there are some recent results on how you can do this, and then you can do a jackknife bias correction. And Han and Nui look at the problem of correcting the parameter estimates themselves. And the idea that this is a jackknife estimator where what you do is you obtain theta hat using all of the data, then you obtain each of the things in the summation using all of the time periods except the one. And if the bias terms are have the same leading terms, this will eliminate the bias up to order t to the minus 2. So this is an interesting area to watch because people are trying to relax assumptions. And unfortunately, it's only known to work so far for not dynamic models, no serial correlation in unobserved errors, and of course the regressors are assumed to be strictly exogenous. The problem is, and you can't have time dummies in your model either, which to me is quite a limitation, because as soon as you allow any heterogeneity over time, leaving a time period out is suddenly going to change the bias properties of the estimator. If you have stationarity over time and no dynamics, then leaving a time period out is going to be fine because you have this strong assumption. But as a practical matter, I'm not sure we should hang our hats on this yet because it rules out dynamics, it rules out time dummies, it rules out serial correlation. And as much as we hate to use things like correlated random effects models, they still, I think, have shown to be somewhat useful. Okay.